Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we are going to discuss about the efficiency and performance of a file system implementation, that is of the disk management, all the algorithms of replacement pages and the paging scheme, buffering scheme, and we will analyze this against the performance cost and efficiency of these algorithms and schemes against our file system implementation. As we know that the disk tends to be a major bottleneck in the file system implementation because it is the slowest component of a main computer system. So the efficient use of the disk can be of the crucial important section while containing this file system implementation. So we need to allocate the disk spaces as readily as possible so that the users can access them directly and sequentially in a faster ways. Now this disk allocation directly depends on the device drivers and the device allocators. Say for instance, the Unix uses pre-allocated Unix file systems or inode structures on the system. So even if the file is empty, then also a amount of space is lost for the storing inode. But before storing the inode preceding in the volume and spreading across it will definitely increase the system's performance. So whether or not we are using this inode for any file length, it will generally improve the system performance regardless of the file size. So now when we are moving to the disk allotment, then we should keep consider of this buffering and paging cache that should be used as a page replacement and memory implement algorithms. Now these algorithms which are being used to implement in the file system for Unix infrastructure to keep a file near its inodes block to reduce the seek time. Say for another example, consider the BSD-free version of the Unix systems, which uses the clustering mechanisms of the file system technology. So it generally reduces seek time as well as access time because the memory is clustered and being in a contiguous memory section, whether in a dot section. Now whenever we are using this clustering scheme, we should keep in mind that the disk access time is lower, but it will become an overhead because we need to keep track of the clusters more and more in the memory or the directory entries. So it will also lengthen the while length varies on the depend on the clustering. So the cluster length varies on depending on the size of the file. If the file size increases, so we increase this file size on the cluster size. Now the large clusters are used to allocate the large files, but the small clusters are used to allocate the small files and the last cluster of a part of the file. That is, a cluster is given to a file, then after that the remaining part of the file is given to the last cluster. The efficiency of the file system also depends on the types of the file that we are using to access. For instance, if we are using the last read or the last write dates of the file, keep up the information about when the file was last modified. So it will be needed this information that the file is then written or rewritten or modified and it need to be backed up to the disk again. Sometimes we also keep information about the last access date, that is to give us the info about the last read information on the file. So that every time a file is read, then the directory entry on the associative disk made to be right about that read entry on that particular file, so that we can know that the memory is read into the disk and then it is modified and again written back to the disk. So whenever a read operation or a write operation happened on that particular file, the disk is being written and read for this particular structure or the entry. Now this file system operations are always performed on a block or chunks of memory. So we need to override that for frequent access of a file, every time the file is read or written, the directory access need to be read and written. So we must calculate and weigh the performance cost of this designing before it is being implemented. as the general system which uses this type of implementation algorithm can be of a performance cost at the time of seek and at the time of access time. Now if we are moving to the next issue, that is a pointer issue. That is a memory used to keep up the pointer size. The most of the operating system uses either 32 or 64 bits pointers. For a 32-bit pointers, the system can support 2 to the power 32 or 4 GB of memory. But the 64-bit pointers can give over large enough memory to not need using the replacements. But the 64-bit pointers need more space to store this keep up of the pointers. So whenever we are keeping the information about the pointers, when we are enlarging this pointer amount of memory, it will definitely keep a large amount or large chunk of memory to keep the information about the pointer. Like the Solaris ZFS system uses a 128-bit pointer, which should never be used for reallocating, as it is more sufficient enough to hold all the memory references for a particular file system structure. Now, one of the difficulties in the operating system implementing and choosing this pointer size and any of the fixed size allocation within the algorithms is that say suppose example say Unix 32 GB memory. When we are choosing a normal MS-DOS version of the previous one, which uses a 10 MB of hard disk as well as the 20 MB of the memory, that is 12 bits are used for the directory entry and the 8 KB is used for the clustering. So this type of memory supports only a smaller amount of memory chunks to point to the data. So now the file systems becomes larger when over the years the versions are being changed and changed. Now our versions in the MS-DOS version 4 or on the modern versions of the Solaris, we use a 32 MB variations because the 2 to the power 32 MB becomes a smaller space for using the 64 MB variations of the pointer. So the 64 MB requires a more space as we have previously told. So now we need a 128-bit pointers which will give us a 272 trillion kilograms or XB bytes, that is more than sufficient to require any memory allocations. So then we can allocate the memory for our considerations, and we should always consider the data types or the file types that need to be accessed in this type of memory references. If the file types are the smaller size, then the smaller reference will be adequate enough. But if it is larger, then we need to make a 64-bit pointer on a 128-bit pointer size to allocate a more than 2 to the power 32 GB or 4 GB memory to allocate it. As another example, consider the Solaris operating system which uses a fixed size data structure, maybe of a system table or a process table. So whenever the process table is full, no more processes can be allocated any file, and whenever the file table or the open file table is full, then whenever no more file is then open for the purposes. Now this processes restriction on this part of file table and process table on opening a file generally reduces the system performance and becomes an hindrance to the operating system. That is why the kernel have to be strictly restrict their limit to this process table and file table because it is of a fixed size. Nowadays, with a version made of 2.5.1 and above, the kernel uses a dynamic allocation for the process table and the file table. That is, the kernel can allocate the files as many times it is needed by a process, or a process can be allocated to as many files as it needed. So it is then allocated dynamically by the kernel and the operating system performance will be generally improved. But generally the operating system becomes a little bit slower because the kernel has to dynamically allocate and deallocate all the memory spaces to the processes and the file systems. But this proficiency in the operating system performance just overlook the cost of the performance and efficiency issue of the slowation of this operating system performance. So that is for the efficiency part. Now we will move to the next part of our section, that is a performance issue. Even after the basic file system algorithm is selected, then also we have some performance issues related with the operating system file system implementation. Now consider an example when we are trying to move to allocate more memory on the same disk. So now we are providing an onboard cache that is providing the same memory location within a same cache memory. Whenever the cache hit is there, so we can access the data directly from the cache. But if it is not present in the cache, then we have to look into the disk that move the disk head to the cache from this disk. Now the cache is then being informed that the disk is using that particular data frequently. So again it will be moved to the cache. So any movement request from this cache to the operating system will then move to the file system algorithm, which will then select that which of the mechanisms to select upon, particularly performing the transfer between the memory and the disk head. And the disk head has to wait after the disk will rotate about the disk, and again it will be moved from the last cylinder to the first cylinder on the first block. So here we are using two types of cache that the data to be needed in. One is a buffer cache, another is the page cache. In a buffer cache, we are assuming that the disk block that is now read into the memory will be kept in there, that it will be again used shortly. So this type of blocks are placed in the buffer cache. Now whenever the buffer cache is become less sufficient to complete any finer grained control, then we introduce the page cache. That is being used in conjunction with the virtual memory systems that provide the disk cache blocks to be divided into finer grained pages that are put into the page cache. So now we can refer to each page rather than from referring to each block. Obviously, referring to virtual memory is better than referring to the physical data block memory, as it can access a more than space that is physically available to the particular user. Now we can use this page cache and disk block cache both for the process pages and as well as the file table. And together it is known as a unified virtual memory system. Some Unix and Linux buffers provide us with an implementation of an unified buffer cache. Now we will implement these two implementations by an unified buffer cache and without an unified buffer cache. So let us consider an example where the Linux uses two system calls, that is read and write. The memory mapping implement and the file system implement. Here the file system implementing uses the two types of cache, that is page cache and the buffer cache. And while it goes to the memory mapping implement, it is using a double cache implementation. First the read and write calls go through the buffer cache. Then it is go to the file system implementation, which is being cached to the page cache. And this page cache will be again cached into the memory mapping system to map it into the actual memory. So here we are using two types of cache mappings, that is doubling the cache, and it is also increasing twice the overhead of doing the computation time for cache. So without unified buffer cache, it will increase the computation and seek time. And with the unified buffer cache, we can allow the virtual memory system directly to interact with this page cache and not using the virtually file system through the buffer cache. So here we can use only one type of caching, thus reducing greatly the seek time and the computation throughput will be higher. So we will see that how this without and with the unified buffer cache can implement it. So first the read and write IO operation is directly put into the buffer cache to use to the file system. So here it will go to the buffer cache, and the buffer cache can also access to this read and write system calls. Now the buffer cache will be put into the file system to actually have this read and write implementation to be done on this file system. So here the buffer cache is using the file system. Now file system can implement this buffer cache, which in turn implement the page cache to actually memory map the IO to the actual main memory from the disk. So the buffer cache will require the page cache as a double caching methods. Now we are not allowing the virtual memory systems to actually interact with this file system. That is why we need this via buffer cache and page cache to be interact with this memory mapped IO. Now this is the section of the without unified buffer cache. So now the read and write using the IO will be definitely moved to the buffer cache directly to react with this file system cache. And now the file system can react with the memory mapped IO directly via the unified buffer cache with the virtual system implementation. Now it will generally reduce the important CPU and IO cycles, as well as it reduces the wastage of the memory that is required for double caching. So here the page cache is not implemented in the unified buffer cache because the virtual system only can perform the buffers to be allocate the memory mapped element to the file system. So in this way, unified buffer cache provides a better environment and performance than the without unified buffer cache in Unix and Linux, both the environments. So whether we are using a sequential access or a direct access, we can say that the LRU algorithm can be used to replace the pages when we are using the page cache for the process tables. Now, when we are using a recent pages that is to be replaced, LRU not become every time an optimal algorithm to follow. Say for when we are performing the writes pages to the particular process. So if we are using the LRU algorithm here, so we cannot use the write pages that is being recently modified, or never we can use it. So it will be delayed or cannot be used at all. So in this way, we cannot use the LRU to be algorithm used in this case. Now Solaris, taken for an example, can use this type of LRU without algorithm to be an page replacement algorithm. Now in this type, the paging cache involves both replacement from the process pages as well as the cached pages. Now there is no distinction among the replacement from the process and the cache, as the process cache and the cached pages are shared in the memory. So whenever an IO is performing more operations on a process, say for example, so it will then replace the pages from the process pages, not the page cache. So it will then deteriorate the performance of the system. Now from the version of Solaris 2.5.6 and 7, it enhances the priority process paging, which gives the page cache a priority over the process pages to be implemented. Now Solaris 8 and onwards, the system provides implementation of forcing the page caches as well as the file system pages to be forced out of the memory and protecting them from doing that. Solaris 9 and 10 implement algorithm that maximizes the throughput of the CPU and minimizes the thrashing. The next performance issue we will discuss is the writes to a particular file. When we are writing to a particular file, we can say that the writes can be of two types. a synchronous write and an asynchronous write. In synchronous write, the caller routines must wait before the device is available and it is then linked with a particular file to be associated. Now the files that is being written to the disk, it will be written to the disk in order, like it will be placed directly in the disk, not in the buffer. So it is maintained this type of synchronous writes when the databases that are to be updated and in atomic transactions where writes to be preserved is consistency. And also the metadata which are used to write synchronously, because it should be properly acclaimed its ACID properties, that is the atomicity, consistency, that the inheritance and the duplicacy. So this can be provided with the synchronous write. With the help of an asynchronous write, we can just write to the buffer of that particular file that is associated with, and the buffer will write it to the disk when it will be find it convenient to do. So other than the synchronous write, the asynchronous write can place the writes inconsistently in any places of that buffer. And it is the responsibility of the buffer entirely to read the disk and write it to the disk of back in and convenient time to do it in proper order. So in many times asynchronous write is avoided to maintain the consistency of a file that is being updated. Now operating system frequently uses a flag in the pages of a process that is to be replaced or modified, that is to tell them that the file is to be write or modified synchronously. If the flag is set for the page of a particular process, then it is said that the page should be modified synchronously. Now, as we have described earlier that the LRU page schemes are not always allowable for replacing the pages within the processes, so two types of paging replacement algorithm uses here. One is a free behind, another is a read ahead. In the free behind algorithms, the page that is just used in the buffer will be removed from the buffer and the next page will then priority to get in the buffer. We are doing this with an assumption that the page will not be used recently, that is already been used once. And in the read ahead buffer, we can replace one page that is the next page to be read and subsequently the other pages that is already brought into the process page table. So in this way we can read the next pages, or we can probably take the pages out of the process in the next memory pages that is to be read next during the operation. So in this way pre behind and read ahead can replace the LRU replacement algorithm as a page replacement successful algorithm. Now the subsequent pages that are to be brought into the memory in read ahead pages are done after the continued page that is currently active in the memory. It can reduce the overhead of keeping small transfers of memory for each track in that particular process page table. So it generally brought into a chunk or all over the track into the memory to keep transfer an entire track that is a subsequent pages with the current page to be brought into the memory. So in this way, buffering the pages into the cache and then doing the disk driver and the disk controller will not only improve the system performance, but it also increases the CPU throughput and reduces the access time. Now the synchronous writes are not always done because the asynchronous writes are generally acceptable because all the writes are not possible to be done synchronously on time to the disk at that moment, because the disk can be busy with the IO tables or any other CPU task. So it has to wait for the synchronous write that the disk is available to be get modified. In asynchronous write, the CPU will be done with the writes to the disk are in inconvenient use. So these are the performance issues that need to get solved before we can implement a file system taking care of the page replacement algorithm, of the write types, the data types and the access types that are made to a particular file. Now, whenever the page is buffered into the cache and the disk driver sorts the output queue according to the files, then it improves the improvement of that particular, reducing the disk head 6. Now, if the writes are more than read, then we go for the free behind page replacement, and if it is read than the write other than IO, then we go for the read ahead page replacement algorithm. So, this way we can address to the performance issues of a particular operating system to improve their performance and then greatly efficiently use the data and the file system that is available to the memory management scheme. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.